This lesson covers the probability of independent and dependent events. A box has 4 cards numbered 1, 2, 3, and 4. Martina will toss a coin once and record the toss as heads or tails. Then she will randomly pick a card from the box and record the number chosen. Give the sample space describing all possible outcomes. Then give all the outcomes of the event that the coin is tossed heads. So I made a tree diagram down here of it, which is kind of fun. So we could have heads and then 1, heads and then tails, heads and 3, or heads and 4. Likewise with tails, tails and 1, tails and 2, tails and 3, and tails and 4 for a total number of outcomes of 8, which I used curly brackets, they're called. And that's what they'd like you to use, enter it on the computer program. And then all the outcomes for heads would be heads 1, 2, 3, or 4. And I looked up different kinds of parentheses for you because I knew it would haunt you. You can also have angle brackets. And like I said, I use curly brackets. And then you got square brackets or box brackets. Next one. Suppose the genders of 3 children of a family are soon to be revealed. An outcome is represented by a string of the sort GBB, meaning the oldest child is a girl, the second oldest is a boy, and the youngest is a boy. The 8 outcomes are listed in the table below. Note that each outcome has the same probability. So you got 3 things happening. The sex of the first child, second child, and third child, which could be girl or boy each time. So 2 times 2 times 2 gives you 8 possible outcomes. Event A, no girls on the last 2 births. So both the last 2 born are going to be boys. That happens 2 out of 8 times, or a fourth. Event B, a boy on the second birth or on the third birth or on both. So second birth, last birth, third birth are also here. We got the first and second one. And a boy was born here on the third birth. So anyway, you got a total of 6 of those happening out of 8. Last one, a boy on both the first and on the last. Well, that just happens twice. The first and the last one born are both a boy. So 2 out of 8 are a fourth. There is a bag of 3 balls numbered 1, 2, and 3. There is also a pack of 3 cards lettered K, Q, and J. As a trial of an experiment, a ball was chosen and a card drawn. The number 1 to 3 and the ball and the letter K, Q, or J of the card were drawn. So you got 3 choices for the ball and 3 choices for the card for a total of 9. So 9 choices right here. This chart is the experimental probability of it happening. The theoretical probability is the exact probability of it happening, just using numbers. Well, there were 9 choices here, so if any one of those 9 happens, the theoretical probability or the exact probability is 1/9, which you'll get if you do a very large number of trials. The larger the number of trials, the closer it comes to being the exact theoretical probability. So letter A, assume the ball was chosen and the card was drawn at random. Find the theoretical probability of this event, both choosing the 1 or 2 ball and drawing the Q card. So that's right here. The number 1 or 2 and the letter Q. So that's 2 out of 9 possibilities. That's the theoretical probability. 2/9 or 0.2 repeating. So to the thousandth place, which is 3 decimal places, it's 0.2222. Then use the data to find the experimental probability. So that's using the chart. So experimentally, when we played the game here, we had 147 and 157 out of the total number of trials, which was 1,375. So that's the experimental probability, which came pretty close to the theoretical probability because that's quite a few trials, 1,375. So it came close to the theoretical probability. And if you did another 10,000, it's going to get closer and closer to it. So the larger number of trials, the greater the likelihood that the experimental probability will be close to the theoretical probability. Number 4. Number 4 you're not going to like. You need to draw yourself a picture of all the outcomes, just like they did on the last one. An ordinary fair die is a cube with the numbers 1 through 6 on the sides, represented by painted spots. Imagine that such a die is rolled twice in succession and that the face values of the 2 rolls are added together. This sum is recorded as the outcome of a single trial of the experiment, of a random experiment. Compute the probability of each of the following events. So you could have, again, that's a dice. It's numbered 1 through 6. You're going to roll it once, then you're going to roll it again. So you might get on your first one a pair of 1s or snake eyes, which add up to 2, or maybe you'll get 2 6s, which add to 12. So the sum of the numbers are anywhere from 2 through 12. So what is the probability that it's going to be a sum of greater than 6? Well, greater than 6 would be the number 7. So 7 and up. So that was, if you add them up, there's 21 of those on a 36, or 7/12. And then what's the probability of an odd number? So I circled them for you for fun. And shockingly, I'm sure you're not surprised, half are even and half are odd. So there's 18 odds on a 36, or a half the time. And then for anyone wondering about what a fair die is, you can make an unfair die. You just take one side of your dice and you put something heavy on it in terms of paints. Different paint have different weights on them. Some paint is thicker than others. So if you were to paint the die or use some sort of heavy liquid on that side of the dice, it'll make it fall to that side more often than the other sides. And then that would be an unfair die. Okay, the next questions want to know about independent and dependent events. So here's an example one. A hat contains slips of paper with the names of boys and girls in a class. A name is randomly selected and returned to the hat. Then another random selection is made. So event A, they said, is the first selection is a boy. Well, there's nothing in the probability of making your first selection that's dependent on anything else happening. You're just picking one out of all of them. So that's independent of anything else. Then event B sometimes depends on event A. And since we returned it to the hat, it's like it never happened. It was returned. And so event B is still independent because everything is still there that was there before. Next one, a box contains pens. Some pens have ink and some do not. A teacher randomly selects a pen and sets it aside. So this time it's not returned. It's taken out of the pool, which will change the probability and the odds. So event A, the first selection is a pen with ink. That's independent, of course. It doesn't depend on anything else happening. And then event B, the second pen selection is a pen with no ink. Well, that got affected because we took one out. So that changes the odds or the probability that we're going to get another pen without ink. So that's dependent on what happened in event A. Next one, at the beginning of each of 2 football games, a coin is tossed and the winner of the coin toss is determined. Event A, in the first game, the home team wins the coin toss. Well, a coin, it's always going to be heads or tail. It's independent. So both of them are independent because neither time nothing happened to affect whether or not you're going to get head or tail. So both of these are independent events. And we've skipped one back here. Oh, we skipped a couple back here. All right, we'll do this one, then we'll go back up to the other one. Okay, this one, we have a litter of puppies consist of black puppies and white puppies. The puppy is randomly selected and removed from the litter. Well, since they removed it and didn't put it back, we've talked about that. When it's removed, that's going to make the second event dependent. If they put it back, then it doesn't change anything. If it's returned to that thing, then this one would have been independent. But the fact that it was removed and not returned, the second event of picking another puppy was dependent. All right, let's go back up here and get number 4. No, I guess it's 5. Okay, number 5. There are 6 acts in a talent show: a juggler, a magician, a pianist, a singer, a violinist, and a whistler. A talent show host randomly schedules the 6 acts. Compute the probability of each of the following events. Event A, a singer is first, a juggler is second, a magician third, and a whistler fourth. This one, the order matters because he's deciding who is first, who's second, who's third, who's fourth. They're making an order out of the acts. So that makes it a permutation. The second one here, any order, they can go up in any order they want. He's picking 4 people or 4 different acts out of the 6, but the order of which they're going, it doesn't matter, which makes it a combination. When the order matters, it's called a permutation, which is the letter P. So it'd be N permutation K. And the formula for that is N factorial over N minus K factorial. Our permutation 6, choose 4. which gives us 360 different possibilities for event A. So they want to know the probability of that exact event happening. Well, that'd be 1 out of 360. For a combination of it, n choose k is the formula n factorial over n minus k factorial times k factorial, or 6 choose 4. All right, so the probability of that one is out of 15. There's 15 possibilities, so 1 out of 15. Let me show you how to do it on your calculators. All right, so find your calculator, turn it on. All right, so the first one, 6 probability 4, well, permutation 4. So 6, enter 6, and then go to the math key. It's the third row down, hit math. Go over 4 menus to probability, and then go down to, we want the P, that's choice 2. Hit enter, and then 4. We get 360. Now we need to do 6 choose 4, or 6 combination 4, so 6. Go back to the math key on the third row down, go over a couple menus here to probability, and so go down to choice 3, combination, so 6 choose 4, and that's 15. So notice there's a lot less combinations than there are permutations. When you do something with the order that matters, you're going to have a lot more choices. If it doesn't matter at all what order they're in, that lowers the number of choices. So that was 15. All right, number 7. A math class has 7 girls and 5 boys in the 7th grade, and 5 girls and 5 boys in the 8th grade. The teacher randomly selects a 7th grader and an 8th grader from the class for a competition. What is the probability that the students she selects are both girls? So we have 2 events happening. She's picking girls from the 7th grade and picking girls from the 8th grade. So 2 events happening, so I drew 2 lines for both events. So the first event, the 7th grade, there are 7 girls out of 12 people in the class. 7 plus 5, 12. The second event is the girl being picked from the 8th grade, and there's 5 girls out of a total of 10 kids in that class. Multiply them together, you get 35 over 120, which reduces to 7 over 24. Or we could use our calculators. So we have 7 twelfths, so parentheses, 7 divided by 12, and then times 5 tenths. Hit enter, and remember you go to the math key and you hit enter, and it changes it to a reduced fraction for you from a decimal, so 7 out of 24. Next one, a bag contains 9 marbles. 2 are green, 5 are red, and 2 are blue. Scott chooses a marble at random, and without putting it back, chooses another one at random. What is the probability that the first marble is green and the second is red? Write your answer as a fraction in simplest form. All right, so the first time he picks a marble, the first event, so I drew a line for it. The first event is picking a green marble. There are 2 green out of 9 marbles. Then the next event is picking a red marble. Well, there's 5 of them. It didn't depend at all on having a green marble. There's, we had a green, then we have a red. So there's 5 red ones. But what changed now is that there's not 9 marbles left in the bag. There's 8 marbles left in the bag. Multiplying across, it's 10 out of 72, which reduces to 5 out of 36. So again, going over that, you had 2 green marbles and 5 red marbles. You had 9 marbles to start with, but you took a marble out, so now you've only got 8 marbles. So that's how you'd get that. I'll do it on the calculator for you. So we got 2 ninths, so parentheses 2 divided by 9, and then 5 divided by 8, and then you hit math, enter, and it's 5 out of 36. Number 9. An internet company surveyed 85 shoppers online, each of whom made one purchase today. The company recorded the type of purchase each shopper made. Here is a summary. 3 shoppers from the survey are selected at random, one at a time without replacement. So they're not putting it back, which makes sense. You bought something, it's gone, so they're not putting the shopper back. What is the probability that one of the 3 shoppers purchased clothing? Oh, none. That's why I highlighted. I lost the word last time too. So none of the shoppers purchased clothing. Well, that would have been buying food, office supplies, or pet supplies. Add them all up, there's 54 purchases. So the first shopper not purchasing clothing, there's 54 of those out of a total number of shoppers of 85. Well, they purchased something, so one of those items is gone, so now there's 53 to pick from, and there's one less shopper now, 84. Then one of those items are gone, so now 52 out of 83. So again, you got 54 to buy from, then 53, then 52. You had 85 shoppers and 84, then 83. So again, put in your calculator, multiply it together to the nearest 3 decimal places, or to the thousandths, it's 0.251. So again, on the calculator, we have got 54 out of 85, and then 53 out of 84, and then 52 divided by 83. So it gives you 0.2511, or 0.251 to the nearest thousandths. All right, number 10. An urn contains 8 red and 6 pink balls, which adds up to 14 balls. 5 balls are randomly drawn from the urn in succession with replacement. That is, after each draw, a second ball is returned to the urn. So this time they're putting it back. So with replacement. The last ones were without replacement. We didn't replace the shopper. They're gone. We didn't put the marble back in. It was gone. So that was without replacement. And this one's without replacement. This one's with replacement. We're putting it back in. So each and every time we're going to have 6 pink balls. So what's the probability that all 5 balls drawn from the urn are pink? Well, each time it's 6 out of 14. Multiplied together, or you could do 6 out of 14 to the 5th. That's a lot quicker. So parenthesis, 6 divided by 14, parenthesis, caret. Caret is on the 4th row down all the way to the end underneath the word clear. So caret 5, enter. So 0.014. Oh, let me see. Yes, I needed to go to the back then. There are 10 women and 8 men with a chance to be on a game show. The producer of the game show is going to choose 10 of these people at random to be contestants. What is the probability that the producer chooses 4 women and 6 men? Round your answer to 3 decimal places. So 2 events happening. The first event is that he picked a woman. Well, chooses 4 women. So he'd be picking those out of the women. And there were 10 women, and he's choosing 4 of them. The next event is choosing the men. So 8 picks 6. And it's a combination because the order of what he picks doesn't matter. He's just picking a total of 4. We're not picking like a president, a vice president, a treasurer. He's not picking specific roles at all, or specific positions, who's first, who's second, who's third. So the order didn't matter at all, which made it a combination. When the order matters, it's permutation, but it's a combination. So it's 10 choose 4 and 8 choose 6, which is 210 and 28. I'll show you again on the calculator how to do that in a second. We get 5,880, and they wanted the overall probability of it all. So then you have to figure out the overall probability of picking the 10 people. And again, it's a combination because the order does not matter at all of what they're picked in. So it's 18 choose 10. When you do that, we get 0.134. So again, on the calculator, we have got 10. Go to math, go over to probability, go down to choose, 10 choose 4, and then multiply that by 8 choose 6. And that was the 5,880. And then I'm going to divide that by 18 choose 10. So 18, and then math, choose 10. And I got that number 0.134, and the number after it was a 3, which is not 5 or more, so it didn't round up, so it's still just the 4. Number 12. A number cube with faces labeled 1 to 6 is to be rolled once. The number rolled will be recorded as the outcome. Event A is the number rolled is less than 5. Well, less than 5 does not include the number 5, so that's 1, 2, 3, and 4. The number rolled is odd. Well, that's 1, 3, and 5. Give the outcomes for each of the following events. If there's more than one element in the set, separate them with commas. All right, we need to take a minute here to talk about the word or and and. Okay, or means either, and it's the union of everything there or all of it. I'll put the word all. It's all of it. We're going to talk about it some more on the next page, but it's everything there. It's all of it. And means both or the intersection. It's a smaller set. It's what's in both of them. It's a smaller set. So this one's a big set because it's everything. Intersection is a smaller set. It's just where they intersect at, what they both have in common. So the union of two sets is the set of elements that are in either set. Intersection is the set of elements which are in both sets. Again, it's a smaller set. So event A or B is, they said or, so it's either or all of it, and it's a big set. So it's everything in A and everything in B. So it's all of that. The next one, event A and B, that means both of them. It's a smaller set or the intersection, so it has to occur in both of them. That's number 1 and 3. 1 and 3 are in both sets. And then the complement of event A, well, event A was 1, 2, 3, and 4, so the complement of it is whatever's missing. What's missing is the 5 and 6. Number 13. 8 balls numbered 1 to 8 are placed in a bag. Some are white and some are gray as shown below. Answer the following questions. Write each answer as a fraction. A ball is randomly selected. What is the probability that the selected ball is gray? Well, you can barely see it, but this one's gray, this one is, this one, and this one. So there's 4 of them gray out of 8, which is a half. Now the next one's pretty interesting. It says, what is the probability that the selected ball is gray, given that an even numbered ball is selected? Given that means it's out of that. Here, the probability was out of all the balls, and there were 8 balls. Here they're telling us it's going to be out of an even numbered ball, and there's 4 even numbered balls, so it's out of 4. So then it has to be both gray and even. There's only one that was gray and even, which was the number 4. So that's 1 out of 4. All right, number 14. If the Venn diagram below shows the 14 students in Miss Kim's class. The diagram shows the membership for the chess club and the science club. A student from the class is randomly selected. Let A denote the event the student is in the chess club. Let B denote the event the student is in the science club. All right, so they did a Venn diagram. These are all the students in the science club. There's 7 of them. And these are all the students in the chess club. And there's, 9 of them. So event A would be 9 out of 14 total students. Event B, there's 7 out of 14 students. And I forgot about poor Teresa. She's not in anything. It says Teresa's not in any club, so she's outside the circles. And there's 3 people that are in both the chess and the science club. So that's this event here. What's the probability of A and B happening? Remember, and was the word intersection. So it's the overlap of them. The overlap is right here in the middle, Laura, Scott, and Kiko. So there's 3 of those out of 14. This one says event A given event B. So that means that B happened. B being a member of the science club. So it's out of the denominator, this number here, this letter here, whatever is after the slash, that is the denominator. And the denominator here is being in the science club. And there's 7 people in the science club. And the top has to be both events happening, the intersection of A and B. So that means they're in the chess and the science